Welcome, everyone. My name is Brandon Rodriguez. I'm joined by my awesome colleague in the education department, Lyle Tavernier, and our special guest, Mark Raymond. We are really excited to host you guys today as we discuss the upcoming Psyche mission. This is a really exciting opportunity to effectively explore what is potentially the a remnant of an ancient kind of planetary core. Could this be some sort of metallic chunk floating through space in a sea of other, debris left over from a solar system formation? We're going to hear a lot about the mission itself and some of the technology that's being utilized to explore this distant asteroid. And then, of course, in addition to hearing this talk, what we're really excited about is hearing from you. So if you are an educator on the line, we'll take some time to go through some of the education resources at JPL through our education department that you yourselves can do with your students, with your classroom, with your children at home, whether you're in the classroom or an after-school program or homeschool. We have all sorts of resources through the education department and NASA as a whole that you guys can kind of build upon the knowledge that you take from today. So you can be part of the Psyche mission going forward and learn everything about asteroids and comets and our solar system formation. So there's a ton of resources for us to play with. But we really also want to hear from you. We want to hear your Q&A, the things that you're excited about for the Psyche mission, the questions you have about the formation of the solar system and planets, and the leftover material that kind of birthed our solar system. So there's a ton for us to cover. And to kind of get that started off, perhaps we can turn over to Lyle, who will talk through a little bit of these education resources.
Thanks, Brandon, and hi, everyone. I am going to switch my screen share so that you can see a few different resources that we have to share today. Some of these are great for teachers, some of these are great for students, some of these are great for everyone, and I will talk a little bit about where each item falls as far as who it is perhaps best for, but you might think that it's pretty fantastic for you, even if you're a teacher and want to play around with the student activity. And so the first thing that you'll see up on the screen is what we call Eyes on Asteroids. This is an interactive simulation where you can, and I'll show you on the screen as I move my mouse around, take a look at some of the many, 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 many asteroids in our solar system. And you'll notice that some of them, each of these blue dots represents an asteroid in our solar system. And a lot of them have names and orbital paths marked with them. So here you can see the asteroid Bennu, which I would probably be really sad if I didn't mention that we visited the asteroid Bennu with a spacecraft, and we're actually bringing back a sample collected from Bennu in just a couple of weeks on the 24th. So less than 2 weeks, actually. But I want to click around, and I'm going to zoom out just a tiny bit here so that we can find the topic of our discussion today, asteroid 16 Psyche. And when I click on it, I got a request to make the screen larger. Let me make it full size. Hopefully you'll be able to see all of that. When I click on the asteroid, I can zoom around and take a look at the asteroid. Now, this is actually an artist representation of the asteroid because we have not visited yet. The best pictures that we have are only a few pixels across. So we actually will change this once we actually get to the asteroid, but it's kind of fun to imagine what it might be. And then I've never noticed this before, but these two craters here and the couple craters here kind of look like a face. So that's what I'm going to imagine it is. But it's fun to imagine what it looks like. And then when we actually get there and get real images from the spacecraft to change our understanding, which is a fun part of science. So this is Eyes on the Asteroid. I'll put a link to this in the chat once I'm done talking over these other resources, but it's a cool one to check out, open to everyone. Definitely recommend you check that one out. For students, we've got a nice one where you can practice your measuring skills and your drawing skills. It's called Draw Your Own Psyche Spacecraft. You can go through, you'll see the materials here. You just need a piece of paper, a ruler, a pencil, a penny. You don't really need a penny, but it helps. And you can create your own drawing of the Psyche spacecraft. We'll put links to this one in as well. We also have a slideshow for students. What is that space rock? We get a lot of questions about what's the difference between a meteor and an asteroid and a meteorite and a meteoroid and a comet. And so we try to answer the questions that students want to know in terms of what is that thing in space? If it's not a planet or a moon, what is it? And this is a great slideshow you can click through and get some of those answers. Again, we'll put a link in the chat for you. We've also got this one. This is designed for teachers, but there is a student version. I love looking at pictures of space. It's really inspiring. And if you are someone like me who likes to write haikus or maybe some other poetry, this is a great way where you can learn about different forms of poetry and then take what you've learned about perhaps the Psyche asteroid or the Psyche spacecraft and write a poem. So let's see, we've also got for teachers modeling an asteroid. So how do asteroids actually form? This is a good one to do in class, but you can also do it remote if you've got students outside of the classroom. And we've got modeling additive velocity. So this is a great one for older students who are learning about things like Newton's laws. You'll probably hear from our guest speaker today about how the spacecraft actually moves through space. And this is a great way that you can calculate just how fast the spacecraft will be accelerating. We've got an article for teachers if you want to really get in depth about the mission, about the asteroid as well. This is a really great one that you can check out. And then last but not least, we have a website, teachers, if you're curious about some of these asteroids that are considered near Earth objects. We have the Center for Near Earth Object Studies, and it's another great place for information about news and where these asteroids actually are. So we will have all these up in the chat. I see that Brandon is already putting a couple in there. And what we are going to do now is introduce our special guest. So let me stop sharing this right now while I introduce Mark Raymond. Mark is the chief engineer, correct me if I'm wrong on that one, Mark, of the Psyche mission. So I'm really excited to hear what he's got to share about his experience working on this spacecraft. I know he's worked on other missions as well. Some of them you can see in his background. I'm sure he'll probably mention a little bit about that too. So I'm excited to hear from Mark. And Mark, I'm going to go ahead and mute myself and listen to you because I know you've got a lot to share and I'm excited to learn some more.
Okay, thank you, Lyle. And actually, I'm excited to be here with all of you students because when I was a student, I would love to have been able to communicate with somebody from NASA. So I became interested in space when I was 4 years old. And I decided when I was 9 that I wanted to become a scientist and work for NASA. But I was in school until I was 29 years old. I know that's sort of hard to imagine ever being that old, but it required a lot of patience. But the reward is I'm getting to do something so cool. I just love it. Every day, I'm doing things that I dreamed about doing my whole life. And Psyche is one of those things, getting to work on a mission where we're going to send a spacecraft in a very short time. In fact, as my watch reminds me, it's in 22 days, 18 hours, and 22 minutes. We're going to send this spacecraft off on a journey through the solar system that's going to take 6 years to get to its destination. So just think about how old you are today, what grade you're in now. 6 years from now, during that time, every single day, the Psyche spacecraft is going to be traveling farther and farther on its journey to the main asteroid belt, well beyond Mars, deep in the solar system, to visit this strange alien world that, as you heard, is maybe mostly made of metal, unlike anything humans have ever seen before. And 6 years from now, you will get to see pictures from it at the same time we will, a place entirely unlike anything we've ever seen before. And the spacecraft will spend then 2 years orbiting this asteroid, taking pictures and making other measurements so we can try to understand how it formed, what it looks like, what it's made of, and what it tells us about the solar system. And this journey is far, far beyond anything humans can do right now. Psyche is going to go more than 1,000,000 times farther away than the space station, more than 1,000 times farther than Earth. And how it's going to do that is really amazing, because we have, oh, and there we can see. So you can, in fact, maybe you can point to Earth with your cursor. So there's Earth. You can see the sun in the center. And so Earth follows this orbit around the sun, but Psyche is going to follow that dashed line. It's going to go way beyond the Earth. It's going to loop around. In 2.5 years, it's going to fly by Mars and just zoom past it, because our destination is far, far beyond Mars. And you can see it keeps going out farther and farther and farther until it gets to the asteroid Psyche. That's going to take 6 years. And to do it, we need an advanced high technology propulsion system to push the spacecraft out there. So we're going to start on October 5th with a big rocket. You've seen lots of rockets launched. This is called a Falcon Heavy. It's a huge rocket. It's really cool, but it's only going to be responsible for the first hour of this journey. So there's a neat picture of it taking off. But 1 hour into our 6-year mission, we leave the rocket behind. And then the way we get to Psyche is with this strange propulsion system that we maybe have a picture of, the cool blue glow, like in science fiction movies, that it produces. And this propulsion system is incredibly efficient. There we go. To me, this reminds me of things I've seen in Star Wars and Star Trek. And it really is a sort of futuristic propulsion system. But unlike in the movies, the propulsion system has a very, very, very gentle thrust. I don't know whether you can see me or not, but the propulsion system pushes on the spacecraft as hard as this battery pushes on my hand. So if I hold a single battery in my hand, maybe you can see that little battery, you've got them at home. The battery is pushing on my hand as hard as Psyche's propulsion system pushes on the spacecraft. Now, how can that do any good? I can hold this battery up all day if I want, although I'm not going to bore you with it, so I'll put it down. But the reason it works is, in the zero gravity of space, the battery just gently pushes every second, every minute, every day for years. And in the zero gravity and no friction of space, gradually the effect of this thrust builds up. And it will allow Psyche to achieve fantastically high velocity, to push itself out from Earth, out past Mars, out to this asteroid, and then to maneuver to get into orbit around the asteroid. And a mission like this would be not just difficult, but virtually impossible with conventional propulsion systems. And that to me is one of the things that's so cool about this, because think about it. We're using a propulsion system that maybe you heard about it, like in Star Wars, you've seen pictures of these cool blue glows. We're going to alien worlds. To me, one of the things that's so cool is we get to turn science fiction into science fact. What could be neater than that? And you get to come along with us, because you're going to see those pictures when you're just 6 years older than you are today. And so you have to wait a while. And during that time, my friends and coworkers, including Lyle and Brandon and others at NASA where we work, are going to be working on making sure this mission keeps going smoothly, controlling the spacecraft, again, when it's so incredibly far away, to guide it on its journey and share the results with you when it gets there. So I think this is super exciting. Every day, I just think about how lucky I am. Seriously, I am lucky to be able to do what I get to do. And I think Lyle and Brandon would say they're pretty lucky too. And I think I'm lucky to be able to share some of it with you and to try to answer your questions. So if you have any, we'll be happy to try to answer them. And I'm interested to hear what you're interested in.
Thanks so much, Mark. This is such a great setup for such a cool mission. I'll give people a chance to kind of type together some potential questions here. While they do, maybe I can kind of start off with just a question I have, which is, if we're able to reach these incredible velocities with the ion propulsion engine versus, perhaps using what has been a conventional means, what does braking look like? What does, if it takes so long to accelerate and you finally reach these top speeds, how does one slow down?
Yeah, it's a very interesting question. There are a couple aspects to it. First of all, if we could go back to the picture that we saw of Psyche's trajectory around the solar system, where the dashed line is the trajectory. What we're really using the propulsion system for is to push Psyche. That's what propulsion means, to push. So we push it. So you don't see my cursor, right? Maybe we could follow the cursor around again. If you could just slowly trace it. That propulsion system is pushing Psyche farther from the sun. Now, it's not strong enough that it can push it all the way around the first time. So eventually the sun's gravity pulls it back in. Then we're going to zip by Mars and steal some of its energy, but keep pushing. I like to describe this as acceleration with patience. It takes a long time to build it up, but notice how it gradually aligns with Psyche's orbit. To me, this is like if your parents drive you in a car where you're getting onto a freeway or expressway, highway, whatever it's called, where you live, and you gradually ramp up to match speeds with other cars around on the freeway. That's what we're doing with the propulsion system here. We're gradually approaching Psyche so that we don't actually have to slow down. Instead, we're matching its speed. So think if you're driving at 60 miles an hour, high, very fast, and there's a car next to you that's driving at the same speed. It looks like you're not going very fast at all. Your car and the other car are going at about the same speed. That's what we're doing with the Psyche propulsion system, is matching the velocity, the speed of the asteroid Psyche. I hope that makes sense. Oh, you're muted, Brandon.
Yeah, that helps a lot and answers probably the exact kind of follow-up question, which is, why do you follow an orbit in the first place and not try to go directly there, right? Your highway analogy kind of holds. It'd be really, really hard to jump into a moving car that's moving perpendicular to you at that kind of pace. Is that right?
That's right. If you're driving, or you're in a car driving this way, and there's another car going that way, that's an accident waiting to happen. Instead, you want whoever's driving the car to gradually change the direction you're going to match the speed of the other car.
Maybe similar, looking at another question here in the chat. You mentioned again the force of thrust is similar to this single battery.
Yeah.
And so a student is asking about effectively the size of this engine. So what is, maybe you could tell us a little bit more about the ion propulsion setup. How is
Yeah.
it, size wise, and how is it generating this force?
Okay. So the actual engine is, it's only about this big. It's not that big, and um, it's the end of a big, complicated system. So when we look at the artist concept of the Psyche spacecraft, the first thing you see is these huge solar panels. So the main spacecraft, if you could bring up a artist concept of the spacecraft, the main spacecraft is a relatively small part of it. I don't see the spacecraft, but maybe that's because I don't have my view set up correctly. Okay, there I see it. Thanks. So you can see the person over on the left there. So the main spacecraft is the yellow and gray thing in the middle, and it's only, you can see, a little bit bigger than a person, kind of boxy. You could fit it in your classroom. Mostly it might be a little bit tall, but most of what you're seeing there, those blue things, are solar panels that collect energy from the sun. They convert sunlight into electricity. And all the systems on the spacecraft, the computer, the radio, the cameras, all the systems need electricity to operate. And so does the propulsion system. So we use the electricity to take the gas that we use for the propulsion and push it out of the thruster at really, really high speed. And maybe you've heard, it's okay if you haven't, for every action, there's an equal and opposite reaction. Or if you happen to be lucky enough to live in a place that gets cold, and maybe you've been ice skating, or maybe you've just seen ice skaters. If an ice skater throws a ball really hard, they're going to be pushed back. Or for that matter, if you have a really heavy object and you throw it hard, it will push you back. That's what we're doing with the propulsion system. We are throwing the gas out very hard, using the electricity to do that. And that pushes the spacecraft in the other direction. And that's how the propulsion system works.
Yeah, that's super helpful. And similar to your answer just now, a question is asking, do the solar panels fold, right? So what does it look like on launch before it's looks like as it is in transit?
They do. If you've heard of origami, or even if you haven't, think of those on each side of the spacecraft. There are 5 solar panels. They fold up and then they collapse against the main spacecraft body. So when it launches, they're all folded up so they can fit in the nose cone of the rocket. Because we saw that picture of the rocket earlier, and you don't see these big solar panels sticking out. There they go. So that's one panel, but all 5 panels on each wing fold up to be that size. And you can see men and women there who are working. They're wearing these funny outfits because we can't allow even a stray hair or any little tiny particle to contaminate the spacecraft. That's why they're in what we call bunny suits, which is kind of a fun thing, so that no particles of skin or hair get on the spacecraft. And they're working with that solar panel. Those go up against the spacecraft, and then a little more than an hour after it leaves the launch pad in Cape Canaveral, when it's out in space, these panels will open up sort of like an accordion unfolding, and it will reach its full width. So when it's in the rocket, it's only a few feet wide. When it gets out into space, it'll be so wide that it's almost the distance from home plate to first base on a baseball field. And in fact, wider than a tennis court. This is a big spacecraft, but it all folds up and fits very nicely and compactly in the rocket. In fact, I can just give you, there's a good view of it. So there's if you move the cursor up and down, right on the right edge, there's one edge of the solar panel. Then it's a long way from there over to the main spacecraft, which is that black thing. And then there's another solar wing on the other side. And in fact, roughly speaking, each solar wing is about the length of a school bus. So this is a big spacecraft. And we need it to be big because the spacecraft goes far away. It's far from the sun. So the sunlight is weaker, right? When you go farther away from a light, that light is fainter. So we need a big area, large solar panels to collect enough sunlight to produce the electricity we need.
Yeah, it's really exciting to see more and more of these solar spacecraft going further and further, right? When I first started at JPL, it was the Juno spacecraft. And, as you're mentioning, the greater that distance from the sun, right, you follow the inverse square law and get less and less light. So how do you power a spacecraft, right? Mrs. Younglove's class actually has a couple questions for you, which are, how will Psyche send pictures? What does data transmitting look like? And how long does it take for those pictures to come back to us on Earth?
Yeah, well, what was the name of the teacher?
This is Miss Younglove's class.
Miss Younglove, sorry. Well, thanks for asking that question. And I'm glad you've got a teacher there to maybe help translate my answers or explain my answers if you don't understand them. But the way we send the pictures back, excuse me, is pretty much the way you're getting this Zoom meeting right now. That is, we use radios. So on the Psyche spacecraft is a big antenna so we take a picture just like the picture that, people get with their smartphones. So it's turned into an electrical signal. We then translate, there's the antenna behind the person so it's covered there with some foil, but it looks like a normal dish antenna that maybe you've seen on people's houses and elsewhere. It's very much like that. So we convert the pictures into a radio signal, transmit that radio signal across the solar system. And, this Zoom meeting is happening instantaneously or very quickly. So you hear me almost at the same instant I'm speaking. But Psyche is going so far away, it could take the radio signals half an hour to travel across the solar system from the spacecraft, past the orbit of Mars, to distant Earth, where they're captured by huge antennas. There are antennas in California, in Australia, and in Spain. These antennas are really, really large. Some of them are 230 feet in diameter. And those capture this very, very, very faint radio signal from far away and turn that radio signal back into the kind of picture that we can look at on a computer. So there you can see Psyche's orbit. It's a long way from there back to Earth. Hundreds of millions of miles.
Maybe just as a follow-up question to that, student Alexis is wondering, will Psyche return to Earth after its mission?
So Psyche will not return to Earth. The reason is because we use all of the propulsion that we have, all of the propellant, the fuel, just like gas in a car. We use all of it to get to Psyche and to maneuver around in orbit there to get all of the pictures and other measurements we have. So we don't have enough propellant to come back. However, maybe in the distant future, or I'm sorry, Brandon, could you say who asked that question?
That was a student, Alexis.
Alexis. Well, Alexis, maybe in the distant future, your children or your grandchildren will go out to Psyche, get the spacecraft, and bring it back and put it in a museum on Earth. So you'll probably be too old to go out there, but maybe your children or grandchildren will. And so then you can visit it in a museum and you can say, wow, way back long ago in 2023, when I was just a student, I heard about this and now I get to see it in a museum. But that's not going to happen for a really long time.
Yeah, I mean, the pace of space exploration, right? It's certainly faster than it's ever been, but yeah, could still be a minute before then.
Each mission takes a long time.
Yeah. There are a few questions from multiple students asking just a little bit of information about Psyche itself. So how big is it? Is it by itself out there, or does it have any like a sister asteroid? And how do we even know that it's made out of metal? Could you kind of talk us through a little bit about why it's of interest?
Okay, so that's a lot of different questions. So first thing, how big is it roughly? So it's sort of like many asteroids. It's kind of potato shaped, but it's about 140 miles across. This is a big place. You know, we heard from Lyle a few minutes ago about on September 24th, we're going to get samples back from a different asteroid called Bennu. But the asteroid that Bennu is that we're getting samples back from Bennu is much smaller. And in fact, most asteroids that are near Earth, so there's Bennu. Asteroids like that are much, much, much smaller than Psyche. So just imagine Psyche is the size of a soccer ball. So think of Psyche as a soccer ball. If Psyche were a soccer ball, that Bennu would be the size of a grain of sand. So this is a big place, 140 miles. You wouldn't want this, say, in your backyard. And in fact, okay, so I was going to give a different comparison because I don't know where most of you live. I was going to give you a homework assignment. Find out whatever state you live in, with your teacher's help, find out the area of your state. How many square miles is it? And then compare that to Psyche, which is, so you may want to write this down so you don't forget it. Psyche is 64,000 square miles. 64,000 square miles. So we see a picture there of Massachusetts. But Massachusetts is much larger than Psyche. This is a very popular picture, but let me tell you why I think it's a little misleading. I wouldn't compare the size of a piece of paper with the size of a soccer ball. Why wouldn't I do that? A soccer ball is round, right? A piece of paper is flat. It's hard to compare them. Now, the diameter of Psyche, from one edge to the other, is just what's shown there. But if you put Psyche between Los Angeles and San Diego, or there in Arizona, it would stand 140 miles high. It'd be way above airplanes. It would reach more than halfway up to the space station. It's a big place. It's got a lot of area. And so I like to think of it in terms of area. So if you, with your teacher's help, or maybe you don't need your teacher's help, I don't know, but find the area of your state and just think about how big it is. Maybe your family is driven around in that state and compare it with the area of Psyche. And what that tells you is there's going to be a lot to see there. Craters and mountains and all kinds of other things that we're going to take pictures of. And normally when you see pictures of like the surface of the moon or Mars or Bennu, which we just saw a few moments ago, those places are mostly made of rock. And some other places in the solar system that we've seen have a lot of ice. But Psyche, we believe, has a lot of metal in it. And we've never seen before a world that has so much metal. And so we don't know what it's going to look like. And that's part of what's so interesting about going there. Because again, in 6 years, Lyle and Brandon and Alexis and whoever the other people were, I already forgot the names. I'm not good with names. I apologize. But everybody else and I, we're all going to see pictures at the same time of a place we've never seen before. Now, part of the reason that's so interesting is not just because we haven't seen it before, but as you heard at the beginning, maybe Psyche, so maybe you know Earth, we live on the surface of Earth, but it's a big place. It's almost 8,000 miles in diameter. If you go deep inside Earth, below most of the rock and stuff, you get to a core that's mostly made of metal, mostly iron and nickel. The exact metals don't matter, but we can't see it. It's way, 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 way too deep to see. But Psyche maybe used to be the core of a planet, small planet early in the solar system that was hit by another one. Oh, good. There's a great picture. Maybe it's even animated. I don't know. Okay, there it is. And what's left over is now that core. What's left over is Psyche. So it's what's left over from what used to be the core of a small planet. Maybe. That's what we're going to go there to study to find out. So we can't see the core of Earth, but maybe we can see the core of a similar small planet that broke up long, long ago.
This is really awesome, and it really helps to see why this is of interest and just how much more there is still to see, right? As Lau pointed out earlier, visually from what we know, this is a couple pixels. The scientific mystery is still very much afoot.
Right. The reason we're going there is because we don't know. What's so exciting about science is we're going to learn new things. And we're all going to learn together.
We probably have time for one more question here, which a couple students are asking kind of a similar theme, which is, if there is all of this floating debris out there, how do you keep the solar panels safe? Is there a risk to them getting damaged? Is that maybe why they're arranged the way they are? We can see in the image behind you, a solar array that is a little different. So, what determines the shape and how we keep them safe as they transport through space?
Okay, so a couple different questions here. First of all, in the movies, when you see asteroid belts, you need to be a great pilot like, Han Solo or somebody else, and you fly in between the asteroids. That's not the way it is in reality. Space is big, and the asteroids are very, very, very far apart. And so the spacecraft isn't going to come near any other asteroids. There may be little tiny things, really little things, the size of a grain of sand or something like that. They may hit the solar array, and if they do, they may damage a solar cell. We have so many that it won't make any difference. So we pick the shape of the solar rays, which you can see here in this picture, in a way that they could fold up to fit in the rocket. And some of the other spacecraft you can see here, like this one and this one, those were just other spacecraft that I've been lucky enough to work on that had solar arrays that were folded differently to fit inside the rocket. So the shape, where it makes kind of a plus sign, doesn't have anything to do with protecting them in space, but rather how they're prepared for launch. Yeah, that's a good view of them. So they open up and open sort of in both directions. I
Yeah.
hope that answered the question.
It's yeah, really, like you had mentioned, kind of likening it to origami, as again, these spacecraft need to get larger and larger on their solar panels. You have to be more creative with how to package these to cover greater distances, right?
Yeah, I'll tell you the way I think of it. I don't know if you've ever seen a dragonfly. I love dragonflies. I think of when the spacecraft separates from the rocket, to me, it's like a dragonfly opening up its big wings and then taking flight. But of course, the solar panels, they don't flap. They're there to convert sunlight into electricity. But I think of it as sort of opening up to go on its way.
Well, Mark, thank you so much for carving out the time. I found this very, very helpful. I'm sure the students and teachers online did as well. Lyle, thank you for walking us through all these resources. To everyone on the line, please remember that the JPL Education website will always be hosting new activities and opportunities just like this. So please keep an eye on the events calendar and the teach section of the website for new activities as they continue to get developed. And hopefully we'll see you again soon for upcoming webinars. Thanks so much for joining us today.
Bye, everybody.